Hello, we apologize for any problems that may occur during this recording. My name is James Perina.
And my name is Rohan Dutt. And our project is different types of seawalls on the effect of protection of buildings.
Our project was created to help figure out which type of seawall would help protect the coastlines against extreme weather, as well as the normal waves that repetitively smash against and erode the coastlines that people count on to keep their land and property safe.
Seawalls are made in various different ways, such as curved, gravity, and steel sheet pile. We wanted to test which basic design of seawall would deflect a controlled wave most effectively so that our shorelines can stay safe.
Our hypothesis is if the seawall is concave, then it'll protect the land better than the other design of walls, because the concave will reflect the wave back into the water and not allow any into the landmass.
During our project, we used various materials, including a waterproofing membrane board, plastic containers, PVC piping to create a stand, a line level, tinfoil, duct tape, and a styrofoam, along with special tools to cut it.
Because of the lengthy process of reading and following the procedures, we will show them shortly, and if you want to read them in verbatim, you can pause the video accordingly.
On the far left, you can see the concave wall. In the picture, you can see the wall smoothly reflecting the water back to the source, showing its effectiveness. Next in the middle, you can see the slanted wall. This wall pushes the water back to the source, but does it in an aggressive way which directs some of the water up and over the wall. Lastly, on the far right, we have a vertical wall. This very basic wall gets hit by the water and does not direct it anywhere but up, causing the water to be very turbulent and go over the wall and into the reservoir.
As per our graph, you can see the results of our experiment. The vertical wall had the most amount of water with a total of 513 milliliters. These amounts were the average of the 3 repeated trials. And second, we have the slanted wall, which allowed more than 50% less than the vertical for a total of 233 milliliters. Lastly, the best wall was the concave wall. This wall led in an amount of 147 milliliters, which is quite less compared to the others.
Based on our data and what was previously stated, we know that the vertical wall was the least effective. This was most likely due to the fact that when the water hits the wall, it sends straight up at a 90-degree angle. Once it comes back down, the water falls on both sides, allowing buildings, which would be on the other side, to be hit. Secondly, we had the slanted wall. This wall sent the water back to the ocean at a 45-degree angle once the water came into contact with the wall. Even though it sent the water back, it was aggressive, and the fast change of movement caused some water to travel over the wall. Lastly, the best one, we had the concave wall. This wall performed the best since it sent the water back just like the slanted, but instead of the rapid change of movement, it did smoothly, so the water didn't come back in over the wall.
In conclusion, we tested 3 different seawalls to see how well they protect the land behind them. Of the 3 we tested, we came to the results that the concave wall was the most efficient, being that it only allowed 147 milliliters of water by out of 2,500 milliliters in the total wave. The other walls were vertical and slanted, which allowed 513 milliliters and 233 milliliters respectively. This data confirmed our hypothesis by displaying the effectiveness of the concave wall. If we were to do this experiment again, we would add another variable to account for flanking erosion. It would be used to compare the effectiveness of the wall against what it does to the adjacent environment. Thank you for watching our presentation.